Hello, my name is Camryn Young. It is August 20th, 2025, and this is my Unit 4 presentation on the article Gene Therapy Comes of Age. So prior to knowing about the steps in gene therapy and how we've gotten where we are today, we need to know a little bit of the background. So a man named Theodore Freeman over 50 years ago kind of broached the idea of gene therapy working on humans by giving potential benefits and challenges that'd be associated with using gene therapy to treat lifelong genetic inherited disorders. And this piqued interest because the idea of fixing lifelong disorders was a great idea. So in the 1990s, a lot of clinical trials began to kind of try and bring gene therapy forward and use it as a permanent treatment for these kinds of disorders. Unfortunately, the results that they were seeing weren't considered promising, so interest kind of died down. But the NIH came out and claimed that this was due to a lack of knowledge of gene therapy prior to the trials rather than gene therapy not working. So there was still hope. So when we go into gene therapy, we see that in the 1980s, the first thing that was used were viral vectors, more specifically Y vectors, which worked really well, but was really risky because it had the unfortunate consequence of causing cancers, which you really don't want to happen to your patients in response to a treatment. So they tried an adeno-associated virus vector, which remained an episome and didn't integrate, which was what was causing the triggering of cancers, but was a smaller DNA size limit and showed effective in certain areas like the liver, retina, cardiac muscle, and central nervous system, but there weren't as effective in other areas. Additionally, a lot of people had antibodies for these associated viruses, so these vectors weren't working very well. So then we go into genome editing itself, which was amazing because rather than just having to add a little bit of DNA in that we had to with the viral vectors, we could add, delete, edit, and regulate, being much more precise and flexible with what we're putting in and when. We used the Talon systems that came out in 2009, and then the big system we've been using since 2012 is the CRISPR-Cas9, which is really nice because it can be flexible and all we need is a guide RNA to connect to DNA at that certain point, and you can edit it however you want. Clinical trials are still open and already beginning to soar above all else and open up doors that we didn't know that was even had a possibility of opening. But it's also opening the doors to a bunch of ethical questions and at what point are we going too far in genome editing. But we have two forms of genome editing that we can do. We can do in vivo and ex vivo. With in vivo delivery, it eliminates this need for cell collection, manipulation, and then reinfusion with the ex vivo because it's happening inside the body itself. And we have examples of the liver, eyes, and central nervous system having some pretty positive effects. So in 1997, an AAV vector fixed hemophilia B in the liver by delivering a gene factor which achieved a stable expression for people who had low levels. This was great, but they still required regular infusions. But eventually, the BIOL caused an unlimited need for regular infusions and is on current trial. For the eyes, it was the first FDA gene therapy to be done in 2017, where there was a AAV RPE65, which improved functional vision and mobility after inherited blindness. And other tests are currently being done related to the eye to see if we can get them better. With the central nervous system, we've been using Parkinson's to deliver dopamine to help with beneficial results. And we've also been doing things with spine muscular atrophy, which is helping gain back a loss of an SMN1 gene that causes that disorder. Ex vivo, we have HSC therapy, where the patient's own bone marrow is re-injected into them after it's pulled and fixed the way it should be. And then we have CAR T cell therapy, where we are using T cells with CARs to specifically go against cancer antigens. Overall, again, a very dense article and a lot of information to collect. But I think that it's not only beneficial to have this done, it is our job as scientists learning about genome editing to use it to benefit the population as a whole. There are definitely ethical questions we need to get into, and we need to have more information on how to properly use genome editing to the best of our ability before it can be available to the public. But once we have that information, I feel like it is our duty to make it available to everyone so people can get these treatments at a okay level.